靠人解出来，这个是 this is bounded by constant。Nobody? Are you sure? 有没有人可以写这个吗？Okay. Let me ask you this question. Okay. You know how to derive like the formula of like a geometric series? Geometric series 就是那个等比数列的那个公式怎么推导？记得吗？Yeah. This one is just like that. It's a very simple one. Okay. So it's that okay. So you let Sn to be this one, right? Okay. So you can multiply this thing by so this one will be right? 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 You can do that, right? No question about that, right? So 这个圈有一个推导那个等比数列那个一样的，you do a subtraction. So it's like this one will be this is this will be only one last term. Yeah, and this part is very simple, right? This part is geometric series, right? Geometric series. 你们会算这个吧 So this one is right? This part is smaller than this one, right? Right? I mean, because in actual like infinite terms, like it's going to be this one, right? And this is like right? So this will give you 2, right? And this one is obviously a fraction, right? Right? When k is greater than 1. When k is greater than 1, this is smaller than this is smaller equal to this one, right? So in other words, your Sn is bounded by 6, right? 这个推导那个等比数列是同样的类似的过程，只不过等比数列两个减下来的时候，前面都消掉，只剩下最后一项。那个，你如果说 if you have learned how to derive like a geometric series like a formula, this is exactly just like that. I mean, so it's so that's why I say like this thing is bounded by a constant. Okay? So the whole thing is you know is a linear term, linear order. Okay? 有问题吗？应该还可以吧。Okay. This is high school math, right? I'm not using like anything you didn't learn in high school. Yeah. So anyway, yeah. 如果你看到这个会出现在高中联考，其实也不是什么奇怪的事情，不一样的。Okay, you see this type of question here in the high school entrance exam. This is also consider medium level problem. Yeah. So I mean, I understand that as you get into college, the level of mathematics is going down. After you grade, in proportion to the time you have to graduate from high school. Yeah, this is really like high school math. Okay. So this is a demo how the field max heap operates. So you can see that at the beginning you have an array. This array obviously is kind of like a random array. Array is a random number. 4, 1, 3, 2, 16, 9, 10, 14, 8, 7. So if you try to represent this as a complete binary tree, it looks like this. And you start to call max heapify from the last node that has at least one child. So that will be the index 5. Index 5. Okay, which is 16. So 67, nothing need to be done. Okay? Nothing need to be done. Okay? And then you look at this one, index 4. Okay? You call max heapify here. Obviously, 2 is more than both of its children, so you need to promote its a larger child, okay, which is 14, to the top. So it becomes like this. Okay? And then, okay, the next one, after you are done, this part is done. This part is done. Okay, yeah, these subtrees are already, satisfy the maximum value. So maximum, obviously. So the next one you go the index 3. Index 3 is again you call the maximify here, and obviously you need to promote 10 to the top. So you do a swap between 3 and 10. And then this part is done. So you go here. Index 2. For index 2, obviously you need to promote 14. Sorry, 16. The larger one of his children to here. So you do a swap. Okay. So 16 goes here. 1 goes here. But 1 it doesn't stop here because you call maximify here again. So 1 is more than 7. So again you need to do a swap. So eventually 1 will appear here. 7 is here. 16 is here. Okay. So the last one you will call maximify is the root. So 4. Okay. 4 again is more than actually both of its children. 16 here. So 4 goes here, and again 4 is smaller than its children, so we'll promote 14 here, and the 4 goes here. And then again 4 is smaller than one of its child, so 4 goes here, 8 goes out. So at the end, this is like the end of how the tree looks like. The corresponding array will be 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. Okay, so from original array like this to here, as we discussed earlier, okay, it takes a linear time. It takes only linear time. Okay, and by the way, like I need to probably remind you, max heap is not so. I mean, it's not yet a sorting algorithm, not yet. Okay, because obviously, like, after you are done with the max heap part, okay, after you finish like building the heap, max heap, okay, building the max heap, you can see that, well, it is still not sorted. Okay, 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. I mean, well, the only thing you guarantee is that the bigger the biggest value appear, okay, at the root. Okay, this is guaranteed. Okay, it does not guarantee like for example, the bigger value appear on the left subtree in the left child. No. So for example here. It happens like a bigger value than that. Okay. But you see here, 8. The bigger value is on the is at the right side. The bigger value of these children is on the right side. Here, the bigger value of these children is on the left side. So it's not like sorted in any in any sense. But we guarantee like the biggest value appear in the root. Okay? So finally, we are able to talk about how to use max heap to do the heap sort. So first, of course, we need to first build the max heap from unordered array. This one, well, we call the building max heap. Okay, that takes linear time to get the job done. And then we know like the biggest value appear as the first element of the array. Okay, that's the final max element, which is A1. You swap the first element, okay, the largest element with AN. Okay. Now, the next element is already at the end of the array, right? It is already in a rightful place because the largest element is supposed to be, because after you finish the sorting, the largest element should appear at the end of the array, right? So after this swap, the largest element is exactly at where it should be. So you can remove that from consideration. Okay, you can remove that from the consideration. So discard node n from the heap. So now you just kind of like you treat index 1 to index n minus 1 as your heap. That's your heap. Okay. The index n is done. Don't do anything. You don't need to do anything for that. Okay? So from index 1 to index n minus 1, it is your heap. But one element violated the heap property, right? Which one is that? You just swap the largest element to the end, and one of the least nodes. Okay, you move that to the first element, right? So that first element, every other places, the heap problem is satisfied, except the root, right? So at the root, you should call, okay, max heapify. At the root, to make sure, it does not violate the heap property. Okay, so that takes how much time? That takes log n, right? That takes log n. And once you are done, from index 1 to index n minus 1, again, you have a good max heap, right? So, in other words, the second largest element should appear at the index 1, right? So you can repeat the process. You can basically like swap A1 with AN minus 1. Put that second largest number in the rightful place. Remove that from the consideration and then try to do, try to fix the heap again from index 1 to index n minus 2. So basically you keep doing that until there's no, you keep doing that until heap is empty. Basically, it's a very, very simple strategy. So each loop, in each loop, except those constant steps, the only thing involved is one max heapify call and the loop, right? Which take log n, right? So you have like, you call this n times, right? Because each time you move the one number to the right place. So it's going to be n log. Okay, so here is like an example that show you how it works. Okay, so this one we already have this from previous. This is like what we already max heap. We have already like doing like building max heap. Okay, for this one, but now, okay, from here we know 16 is the largest element, so we do a swap. Okay, between 1 and 16, and then, well, actually, when we have to do a swap, like a 16, we don't need to deal with 16 anymore. 16 is outside of the heap now. Okay. Well, even though 16 is still in the array, in some, of course, 16 is still in the array, but we don't consider 16 as a part of the max heap. Okay. So now that 1 appeared in the loop, so we need to do max heapify A1. So eventually become obvious that 1 have to swap with 14, and then 1 again swap with 8, and then 1 gets swapped with 4, so we come back here. Okay, and then we do a swap between 14 and the 1. And then 14 is the second largest element. So, we keep that 16, 14, here. Okay, and then swap 1 to here. And then we call max heapify and loop again. So 1 gets swapped with 10. And then this one again gets swapped with 9. So 10 appear as the base number. Okay, and then, okay, we need to, the 10 is the third largest element. So we swap 10 with the last element in the heap, which is 2. So 10 gets swapped with 2. So, and then we remove 10 from the consideration. So we have like 10, 14, 16. 2 appear here. So we call max heapify and root. So, well, 2 gets down here, and then 2 gets down here again. So 9 appear here, 3 appear here. So, at the end, so we keep doing that, So every time we do the max heapify, finish the job and then we can do a swap to put one number in the right place. So eventually, okay, you are building the sorted, list of numbers, from the largest one down to the smallest one. Okay. That's it. And the running time, as I said, we will call max simplify n times. So, every iteration involves a swap and the max simplify. The swap takes constant time. Max simplify takes log n. So it's n log n. Okay. So, so far, how many advanced sorting algorithm have we talked about? Okay, let's first make it clear. Okay, when I say advanced algorithm, I mean that the algorithm that can solve the numbers in n log n complexity, time complexity. Merge sort and heap sort. But probably not quick sort, because quick sort, the worst case is n squared, right? But if we say if we also include expected time complexity, yeah, and then quick sort is included. Okay? And we talk about insertion sort, right? And you should have learned bubble sort from your freshman year, right? Freshman year, when you learn how to do programming, bubble sort. I mean, 施国珍老师要教会你bubble sort，我们是，不高就大概是你们第一年的那个是谁教的？谁教的？啊？我老师，对，为什么？必须的，高就bubble sort，right? I believe. Yeah, I mean, bubble sort is kind of like an example used to demonstrate the loop. Okay, so if it's I don't think I need to talk about bubble sort in algorithm, right? So yeah, so yes, I mean in the programming assignment, okay, you need to implement every one of them, okay, including some additional non-comparison based sorting algorithm that we are going to talk about in the next chapter. Okay, in the next chapter. Okay, just want to give you a head up. So that's it for this chapter. So we have a little bit less than 20 minutes. So I will probably talk a little bit about yeah, and by the way, because it is also about time. Okay, I will assign a second homework. Okay, assignment later today. Okay, and so yeah, because I think let me check. I believe we finished 2 chapters. Let me double check. If not this week, it will be next week. Okay. And also, remember, the midterm will be held in the midterm week. Okay, in the midterm week. which is the 8th week, is that right? 就第8周啊 the midterm will be held in the 8th week, okay, of our semester. So which week was that? Which week was that? How many weeks left? 确认一下，今天是第几周？今天是第4周。4月15日，今天是第4周。Okay, it's the 4th week. Yeah, so we still have a little bit of time. But I would like to bring your attention. We will have like a midterm. So yeah, I think I will assign like a homework assignment next week. I think we should have like enough time. So on the 8th week, we will have the midterm. Okay, so it's April 15th, right? Middle of April. Okay, so please take note. Okay, take note. Okay, this lecture 5. Okay, first we'll discuss like lower bound of the sorting algorithm that is based on like a comparison. Okay. And then we are going to talk about two very famous linear time sorting algorithms, okay, that are not based on comparison. So as I just mentioned, okay, all the sorting algorithms we have discussed so far are what we call comparison-based sorting algorithms. Okay, we use the comparisons to determine, the relative order of elements. Okay, so this includes insertion sort, merge sort, quick sort, heap sort, okay, and bubble sort. We didn't talk about bubble sort, but bubble sort also fall into this category. Okay, so the best worst case runtime that we have discussed so far for this comparison-based sorting algorithms is NLog. Okay, it's NLog. But our question is that, okay, is NLog the best we can do, okay, for comparison-based sorting algorithms? The answer actually is yes. Okay, the answer is yes. But how do we make sure this is the case? Okay, we call this is there's a argument. Okay, it's a proof that it's based on decision tree. Okay, how do we mean? Let's assume every internal node we have a tree. Every internal node indicates a comparison between two numbers. Okay, if the first number is smaller than the second number, we go left hand side. If first number is greater than the second number, we go right hand side. Okay? Very simple, okay, idea. Okay. So this is an example of like sorting three numbers. Okay. So if you want to sort three numbers, so you have only three index, right? 1, 2, 3, right? So based on the relationship between the first number and second number, you may go left, you may go right. Okay? So say you go left, that means like 1 is smaller than 2. The index 1 is smaller than index 2. And then 2, 3, we compare number 2 with number 3. Okay? Sorry, the second number is third number. So if second number is smaller than third number, so you go here. Because obviously, you know for sure, okay, 1 is the smallest element. Okay, this 2 is larger than 1, but smaller than 3. So 1, 2, 3. That's the order of these three numbers. Right? Okay, logically speaking, that's the order of these three numbers. Okay, but if 3 is more than 2, then you have to have one more comparison. Because obviously, like 2 is the largest element, but 1 and 3 we don't know. So you compare 1, 2, 3. If 1 is smaller, it's going to be 1, 3, 2. If 3 is smaller, it's going to be 3, 1, 2. Right? Right? We need like additional comparison to figure out the relationship of these three numbers. Right? Okay, same thing here. If we go to the right, okay, 1, 2 is not smaller than 1. And if 3 is smaller than 1, then we need one more comparison. Otherwise if 1 is smaller than 3, then we already know it's 2, 1, 3. Okay, if 1 is larger than 3, then now we need to compare 2 and 3. We go to have these 2 results. Right? So here is like you figure out like the relationship of these three numbers. Like all the different comparisons for you to for us to figure out like the relationship of these three numbers. Right? So once you know their relationship, obviously, knowing their relationship, for example, if you already know, okay, 3 is the smallest one, and then it's the first one, and then 2 is the index 2 number is the largest one. Well, you just do linear order, linear times 1, you get your sorting done already, right? Okay. So the first thing is to figure out like the order of these numbers. And these comparisons are necessary, right? These comparisons are necessary. Like if you try to skip any of these comparisons, your sorting may fail, right? Your sorting may fail. For example, if you skip this one, you have trouble figure out which case your numbers belong to, right? So none of these comparisons can be skipped, right? So that's what we meant, This is for 3 numbers. You can generalize this to n numbers, right? You can generalize easily. You can generalize this to n numbers. Okay, for this what we call decision tree. Okay, so the idea is that once we have this in this example, if we have these 3 numbers 9, 4, 6, 9, 4, 6. You compare first one with the second one, it turns out the first one is larger, so you go right. And then you compare the first one with the third one. The first one is still larger, so you go here. Okay, and then you compare the second one with the third one. So the third one is, the second one is smaller, so you go here. So it's a true 3, 1, 1. Yeah, the smallest element is the second. The second smallest element is the third one. Okay, and the largest element is the first one. Right? That's exactly what I was talking about. And then, once you know that, you can easily get like the sorted result, right? So it's 469, right? Just once you know the case, you can just map those numbers into the sorted order. Basically, just each leaf contains a permutation to indicate that the order, okay, of these numbers has been established, like the relationship has been established. Okay? So, and as I said, this internal node comparisons, none of them can be skipped. So basically, you could use this decision tree to model any comparison-based sorting algorithm. Okay, you could use the decision tree to model any comparison-based sorting algorithm. You could use that to model, for example, bubble sort, insertion sort, merge sort, quick sort, like a heap sort. Any sorting algorithm, as long as it's comparison based, each comparison basically that give you more idea how those numbers are ordered. Okay? So if you can understand this, then the question is like this: how quick your algorithm can run, right? So your algorithm, because we are talking about worst case complexity, right? So the algorithm, if you consider worst case complexity, that's basically the height of the tree, right? The height of the tree indicate like the number of comparisons necessary to make sure that we achieve like the final result, which is like we are able to solve these numbers. Okay, so the running time of algorithm is the length of the path taken. The worst case running time is the height of the tree. Okay, so that's the idea here. So if you agree with this idea, think about this. How many leaf nodes do we have for n numbers? It's going to be a permutation of n numbers, right? So n factorial n, right? You have this many cases, right? And each permutation is distinct, right? Each case is distinct. Each case is a distinct leaf node, right? Each case indicate a different leaf node. So for a binary tree, okay, it has like a node, like at least like n factorial n leaf nodes. Okay, then the height of the tree, at least is larger or equal to log of n factorial n. Log of factorial n. So what is this number? The factorial n is n divided by e to the power of n. This is like if you know Sternbach formula, like this is an approximation for factorial n. Okay, and I will for this I will skip the math. Okay, because this is not high school math. But I suppose like your calculus should cover this part. If not, you can do a Google. Okay, this is like something that's supposed to be covered by a calculus. Okay, but I I don't have time to, because this is not as easy as like, I just write like a few lines on a whiteboard and be able to tell you why it is the case. So you guys can go, Google the Stirling formula, okay, to understand why vectorial n can be approximated by this one. But I will skip that here. Okay. So this one is greater or equal to this one, and then because it's a log, right? So it's going to be n log n, minus n log e, right? N log e is 1, right? So n is just a linear term. If you consider like the order, this n will be absorbed by this one. So it is omega n log n. Okay, because it's a greater or equal. Okay, so with that in mind, okay, it gives us the insight that any comparison-based sorting algorithm, the complexity cannot be lower than n log n. Okay, otherwise it violates the decision tree property. Okay, so it tells us that the heap sort, merge sort are asymptotically optimal comparison sorting algorithms based on this idea. Okay? So far so good, right? Okay, cool. So next week we are going to discuss like non-comparison based sorting algorithm and some additional stuff. Okay, probably like that's it for today. Any question? Yes. 大声。